Discussing Shunyu Yao's PhD thesis, I think it's one of the more important theses that came across the AI community in the last maybe year at least, if not even more. And in particular, I want to talk about two things here, about agentic systems and about tree of thought. I mean, there's a lot more here, of course, and I certainly can't do justice to a thesis that has taken 5 years to be written and has had a big impact in like a 20-minute conversation or less. But nevertheless, that's what we do here at Orange, at the Not Even Wrong podcast. We try to distill knowledge and give ourselves and our listeners a little bit of a sort of a short, concise, and hopefully also transferable tidbit of knowledge that we consider important. Now, why do we discuss a PhD thesis by an AI researcher? A couple of reasons. One is curiosity. We're in the knowledge business, so anything that opens up our knowledge about AI or generally intelligence, I think, is interesting anyway. I mean, it's research in AI is becoming more and more a sort of a cross-disciplinary approach between epistemology, philosophy, cognitive science, in engineering, and even physics. So it's really super interesting. Number one. Number two, we are heavily invested in robotics through Tesla and NVIDIA. So we're obviously interested in any kind of automated decision-making, real-world decision-making, even digital decision-making, large language models, reasoning. So those kind of things which Shunyu's thesis is really a foundation on. And I think the recent excitement about agentic models, about O1, the model that OpenAI sort of launched recently, about reasoning and the idea that you can have AI learning how to do inference without changing necessarily its parameters around its knowledge base. So not just sort of using the traditional AI, which is you have a bunch of weights and then you're exposed to the environment and you act based on the environment, but a very different type of approach where you look at the world, you have your knowledge, your weights, your condensed knowledge of, let's say, the world through what you learn in reading the internet, and then you reason throughout this knowledge. So this is the fundamental idea of Shunyu Yao's thesis. Here's a quote from the thesis. We define language agents not as agents with textual observation and action spaces, but agents that process observations to actions via internal mechanisms of natural language reasoning. So there's obviously a lot to unpack here. So we're talking about agentic systems. First and foremost, we're talking about agentic systems. This is an agentic system. So we have a large language model which can act as a distributor of workloads. So it can be an agent that helps solve a problem by distributing workloads. So for example, it helps finding the right item to buy on Amazon by searching the web, comparing, looking at prices, looking at objectives, and then finding you the right place. There's this concept of one-click shopping as opposed to one-click payments, which means that you should be able to tell your agent, I want to buy a running shoe, and it should just offer you, this is your shoe. Like, don't think too much. I did the search. I combined all your previous purchases. I know what you need. It's, autumn. You're going to need it for winter running. This is your shoe. So that kind of thing. That kind of thing is, in my opinion, what agentic systems will morph into, amongst other things, of course. So Shunyu goes further and says, quote, new methodology for agents that can reason in language, to which my work has made foundational contributions by designing simple general methods that connect language model reasoning to agent acting and planning, with the key idea that reasoning can be seen as internal actions for agents, end quote. So the point here is that he talks a lot about reasoning. He talks a lot about internal states of an agent. And I'm going to try to dissect that here a little bit more. So there's really three fundamental things that I caught on in this thesis. Okay, number one, agentic systems as a concept. Number two, tree of thought, the idea that you can have reasoning as an agent can reason. And number three, which is what they call Coala, which is a sort of a framework and architecture for exactly that, for a reasoning agentic system. This is not even on podcast. It's October 6, 2024. This is Crimdelco. It's a Sunday. There's an update for the year. We're up 22.4%. The market's up 20.4%. We're outperforming by 2%. So Shunyu Yao's PhD thesis, the links is in the show note. Also, his PhD defense is in the show note. Is certainly one of the pivotal points, in my opinion, in recent AI history. It's one of those things that really excites me because we often talk about this on this podcast. We like to see ourselves sort of at the crossroads of science, technology, and entrepreneurship. So where these things sort of, where the Venn diagram intersects, that's where we like to invest. So not progressed enough that 10 businesses are already doing it, not far away enough so it's really just a science project. It has to be something that is sort of in between and where the opportunity lies to transfer the know-how that scientists created into technology and then businesses. What's the difference? What is science? What is technology? What is business? Let me just sort of digress a little bit. So science is the process of trying to uncover what nature has to tell us. Like whether it's physics, chemistry, robotics, it's always the same thing, right? It's okay, what's actually going on in nature. And in Shunyu's case, I think the scientific work here is particularly in the realm of cognitive science and in general cognitive architectures. Okay, how do intelligent systems make sense of the world? How do they do inference? How do they act? Those are the kinds of questions that scientists first have to answer. Technology is what most of robotics and AI is all about, which is you take those, let's say, take the idea of short-term and long-term memory, you take the idea of textual reinforcement learning instead of scalar reinforcement learning, and then you actually implement it with tech. You use vector databases, latent space representations, all these kinds of things. You do searches, you have efficient memory, you have efficient hardware, you do neuromorphic compute, whatever it takes to execute your plan. And then, of course, the entrepreneur turns that into a business, which really means you have to do all of this at a certain cost point and then be able to make more money than you spend, so you have a business. So we see ourselves at the crossroads of those three bubbles, so the Venn diagram that intersects all of those. And whether that happens in a startup or whether that happens in a blue chip company like NVIDIA is not of the most importance for us. It is a little bit important. We prefer the large companies like NVIDIA with lots of liquidity and lots of also opportunity to make money in other ways, have more synergies, let's say, than a startup. But there's nothing wrong with startups, of course. So let's talk about what does Shunyu actually mean with agentic systems? Why is this such an interesting idea? And he mentions in his PhD defense, he talks about the von Neumann computer architecture. Okay, the von Neumann computer architecture, which is really what our computers today are based on, fundamentally is based on that you have an input-output, and the input is being inputted into arithmetic logic unit, ALU, which processes numerical problems, and the results are then being fed as output into some sort of memory, and you have a program also that runs these things. So that's kind of the architecture that we live in. So input, processing, output, and there's other architectures like data flow architecture, for example. But you could have a new kind of computer architecture which is based on large language models, which is more of a sort of react to the outside world. So you get the input also, but it's not an input in a sense of a ticker tape, for example, like in the old days, or a punch card or some code. But the input is, let's say, sensual experience or textual input. Please go wash my kitchen, right? And then the idea of the agent is, okay, how can the agent approach this? And the approach is, and this is where the
actually the third level, the Coala, the cognitive language, I don't know what it stands for, basically cognitive architecture for language models. Think about it this way, that you're using language as a representation of states and semantic memory levels. So what do I mean with that? What I mean with that is that you have a sort of intermediary representation of semantic knowledge in terms of words. So instead of having everything in scalars and numbers, you represent things like, for example, there is a door in the kitchen. This is a verbal representation of reality, which can be stored in long-term memory. And then when the robot, let's say in this case a real-world AI, a robot is moving in the kitchen, it can access the long-term memory and say, oh, there's a door, so therefore I can exit the kitchen through this door. So things like that are just if you want, it's like a hack. So why is textual representation in long-term memory even useful, and why is textual reinforcement learning more interesting than scalar reinforcement learning? Well, because you have semantics. You have, if you want to really boil it down, you have a vector database, you have a vectorized representation of reality, and you can use the relative distance of vectors to express semantic knowledge. And with that semantic knowledge, you have a little bit more knowledge of the world. You have a little bit more context. And this is really where this PhD thesis is going, in my opinion. This is what agentic systems combined with Coala and tree of thought really mean, is that we have data. So data is data, right? Let's say if my self-driving car drives, it sees the world as it sees it. But we can represent that data in different ways. So the internal representation of that data itself is knowledge, right? I can say there's a door next to the kitchen. That's knowledge because it allows me to do inference based on, like, I can actually exit the kitchen through the door. If my representation is just pure scalars, then that needs to be learned. It can still be learned. I can learn that I can exit through the door, but there's a certain shortcut by having textual representation, which also is learned, but it's a more compact, I guess, if you will. A language is a compact representation of reality. It's a shortcut, it's a hack, and therefore, in my opinion, useful. And that's, I think, what Shunyu really tries to bring home with his PhD thesis. So what is tree of thought? Tree of thought is, think about tree of thought as a sort of reinforcement learning game internally, where you have, so you train a model, and the model learns learns everything that is to know in the internet, and it stores that knowledge in a vector database in latent space. And what's that useful for is we have structure, and we have semantic understanding. We know that the door and a kitchen have a certain relationship to each other, the same way that a mouse and cheese have a relationship and a mouse and a cat have a relationship. So these are not just scalars. There's some meaning, there's some semantic meaning. And then if my model sees a house, a mouse, and a cat and cheese, it will be able to infer from there that the mouse will try to go eat the cheese and then probably be chased away by the cat. So it will have that knowledge without having to go through another million iterations to learn what's going to happen. It will already a priori know that this is going to happen, very similar to how humans learn. And the tree of thought now is this idea that you have, when you're exposed to a certain problem. For example, write me a poem with the following words in there, tree, sunset, love, my girlfriend, and maybe a couple other words. So it has a couple of ways to do that. And the way it decides how to do this is it goes through its own semantic sort of tree search. It does its own semantic tree search. And how does it decide which branch of the tree to go? It decides that based on its long-term semantic memory, and that is done through some sort of reinforcement learning type exercise where it goes through a couple of versions and then has a way to decide which one is better, and then learns from that, and that in that sense learns how to reason. So there's this short-term internal representation of knowledge which can change based on the situation, and then the long-term representation which is a little bit more fixed. This is the fundamental idea. So it's kind of the system 1, system 2 Kahneman type system. Shunyu talks about this. He borrows from the cognitive literature and the psychology literature, and I think that's just like a PhD thesis should be. It's an inspirational thought. There's a lot of engineering around this. I'm not going into this in this presentation, but I just want to mention that there's certainly a lot more than just ideas here. There's real engineering, real tests, real evaluations, and just talking about evaluations. Okay, when we have, let's say, tree of thought, or when we have agentic systems in general, the way we test whether the approach is right, we do automatic evaluations. So automatic evaluations is just a fancy word for maybe reinforcement learning, or doing an internal process where we evaluate our own actions and then use the feedback to change our actions or improve our actions. This is reminiscent of Professor Mirhoseini's large language monkeys, where you have this idea of self-correcting semantic decisions, semantic actions. Talks about this also in her presentation, where you have automatic evaluation. I think this is key. Particularly also Shunyu talks about coding as an application here. And the beauty about agentic systems and coding is that agentic systems are very good when they can self-grade themselves. Self-grading is fundamental. Whether it's tree of thought or any other kind of agentic system approach, you need to be able to self-grade. So you need to be able to understand when your approach is better than, which approach is better, A or B. You need to be able to do A/B testing, A, B, C, D, E testing. And in order to do that, you have to be able to grade yourself. So the grading itself, of course, can be learned. And that brings us into the circle of reference of, okay, what is it I learn? And the way I do inference is by learning how to grade my own actions and improve my actions based on the grading. But then how do I learn the grading? Well, that in itself is based on actions. So there's a certain circle of reference that I don't want to go into right now. I just want to mention this. We're certainly sort of in a Gödel, Escher, Bach situation here. And that's not something Shunyu is talking about. I am in conversations with Elijah Milgram from the University of Utah, a philosopher that talks about personal identity and inference of humans. And I think I hope to gain some knowledge there. The last thing I want to talk about in this particular episode is now Coala, which is this cognitive framework. And what that really means is, okay, once we establish the idea of agentic system, once we establish the idea of self-grading and tree of thought, and a sort of verbal grading and semantic representation of the real world and semantic representation of reasoning. Once we have all of that, then what kind of architecture do we build? So, for example, we have the idea of memory, which is working in long term, and we decide how do we structure the short-term memory, how do we structure the long-term memory, how does the agent update its weight in the short-term memory, how does it learn updating the long-term memory. Those are architectural decisions. Modularity, we have perception, problem solving, reasoning. Certain actions belong to the short term, certain actions long term, and certain actions are hybrid. And then the idea of learning per se, how do we learn? Do we learn through reinforcement learning, or do we have other techniques of learning? So those are all conceptual, architectural decisions that Shunyu is offering here. Again, worth reading, particularly for engineers, of course, implementation types. Here at this level, we just want to leave it at that and just say, look, this is a really nice example of a PhD thesis that, in my opinion, has a lot of impact. So to summarize, there's really three things that Shunyu is pointing out. One is the concept of agents as semantic decision makers with actions. The tree of thought concept, which is the ability to evaluate a tree search type reasoning based on semantic discrimination. In other words, you instead of just having numbers and scalars, when you do evaluation of which tree is the best, you have a bit more complicated, maybe vectorized database, or in other words, a language-based discrimination structure. And third, he talks about Coala, which is now a sort of a comprehensive framework of how to establish agents, reasoning agents, how to structure memory, how to structure the modularity, what reasoning means, what action means, what perception means, what problem solving actually means. And maybe as a final word, I think this is also definitely a stepping stone towards Sergey Levin's Robinson Crusoe robot. Actually, there's a quote in the thesis where he says, or maybe I picked it up from somewhere else, but no, actually this is Elia Milgram, but very similar. He says that a system, if you build a system that is able to deal with unseen edge cases, you want to have a system that can reason about its own reasoning structure. And this is, of course, what Shunyu is trying to build here, the first stepping stone, and I think that's where we're going as an AI community. Thank you.